Hey guys, okay, so here's the first set of a series of instructional videos that we're going to do as we transition the class to a little bit more self-paced independence. Okay, so today we're going to talk about ionic bonding. Ionic bonding is a type of chemical bonding that involves electrostatic attraction, okay? I want you guys to remember this word, electrostatic attraction, because all it basically means is that if you have a charge that is opposite, right? For example, if you have a negative charge, you know that that charge is going to be attracted to a positive charge because positive negative charges attract. All right. Now, when it comes to terms of ionic bonding, what we're seeing is that we have atoms that are bonding because of those charges. This is where we get the term ionic bonding from. And ionic bonding comes from cations. So we already know, or we should know, that a cation, all right, let's see, let's erase that. Sorry about that. You know, this software like always completes my C's into an O. I don't know why. Okay, so we know that a cation is an ion that carries a positive charge. So it's a positive ion. Okay. The other type of ion that we looked at was an anion. An anion, you know, that is a negatively charged ion. In order to form an ionic compound, right? An ionic compound is going to require both. So if I want to make a compound, ionic compound, you know it's going to be a union between a cation and an anion, right? So it's going to be a cation and an anion, right, coming together. What we have to figure out is know which one is which and specifically know what charge they're going to carry. So we're going to take a look at that today, okay? Here we have our table of our ionization energies because we're going to use that to determine what type of ion we're going to make, and we're going to do a couple of examples. Okay, so I'm going to scroll up a little bit. All right, should be working on your guided notes. Okay, all right. So the first element that we're going to look at is sodium. Okay, we're going to take a look at sodium. Let's go ahead and do the electron configuration for sodium. This one I'm going to do with you. The other one should already be done, but I'm going to zoom in a little bit so we can see exactly what's going on. Okay, let me make my pen a little thinner. All right, so sodium, we should already know that it's going to be a 1s2, 2s2, 2p6, okay, 3s1. So this is the electron that represents sodium. Okay, so we should already know this. Okay, I'm going to zoom back out here real quick. All right, so let's take a look at sodium. Let's take a look at sodium. Based on the electron and the electron configuration, I can already see that the primary quantum number for sodium is going to be 3. The azimuthal quantum number is going to be the s orbital, so that's going to have a value of 0, which makes the m sub l sub 0. And the spin is going to be just a positive 1/2. Okay, so these are the quantum numbers for sodium. Now, sodium is in the third energy level, and here we have a half empty subshell, okay? And then here we have a completely empty orbital. So sodium has a choice whether it's going to go out and find all these electrons, right? Pick up electrons, or if it's going to drop any off. That's where the ionization energy comes in. This element here, this little dot right here, this guy represents sodium. So as you can see, sodium has a very, very low ionization energy. So because it has a low ionization energy, I can already tell that sodium's not going to pick up electrons, right? Sodium's not going to pick up electrons because it's just not energetically favorable. Plus, it only has this one electron to get rid of. So I can see, okay, right off the bat, that sodium is going to oxidize. Sodium is going to oxidize. If you don't remember what this means, it means that it's going to drop electrons. It's going to drop electrons. So if sodium drops that one electron that it has out in the valence shell, right, like the Lewis structure says, right, it's got that one electron out here. If it gets rid of that electron, well, now sodium is in a position where instead of having 11 protons and 11 electrons to have a neutral charge, now it has 11 protons and only 10 electrons, right? So what ends up happening is we end up with sodium with a +1 charge. So sodium forms a cation, and the cation looks like this, sodium plus 1. Okay, sodium plus 1. So based on what we see here, we can see that sodium is going to oxidize. Let's go ahead and fast forward a little bit here, or let's go to the next one. And let's take a look at chlorine. So you can see chlorine's already done, okay, the electron configuration. So let's zoom in a little bit so we can see exactly what's happening. All right, so chlorine is here, okay? This is the electron that represents chlorine. So you can see that the third energy level, the third shell, is pretty much almost full. It has 7 valence electrons. It only needs this 1 valence electron in here to have a full shell. So based on that, right, let's go ahead and take a look at the ionization energy of chlorine. Let me zoom in here a little bit. Okay, so chlorine is this element right here. Now you can see that chlorine has a pretty high ionization energy, right? Now, what that tells me is that the hold of the nucleus is pretty strong on the electrons, and it's not going to let very many go, right? And if it does, it's going to take a ton of energy to do that. So chlorine is not in a position where it's going to drop electrons. We can see that chlorine is in a position where it's going to gain electrons. So a high ionization energy, right, with a almost full subshell, right, in the p orbital, we can see that chlorine is going to pick up electrons. So chlorine is going to pick up. Okay. All right. So let's take a look at this. We can see already then that chlorine is going to reduce. Now, because it only needs 1 more electron, it's only going to reduce 1 electron, right? So chlorine, right, is going to have a difference in the number of electrons. Chlorine normally has 17 electrons and 17 protons and 17 electrons, which gives it no charge. Because it picked up 1 extra electron, now it's become an ion, where now it has 1 extra electron, resulting in a -1 charge. Therefore, chlorine forms the anion -1. Chlorine -1, okay? Sorry about that, guys, the bell. Okay, so now we have our 2 ions. How do they come together? How do they bond? Okay, let's take a quick minute here, and I'm going to go ahead and just give you guys take a look at the primary quantum number of chlorine. So chlorine is also in the 3. Chlorine is in the in the p orbital. So the value of L is going to be 1 for this guy. It's in the last subshell, so the value of M sub L, or the magnetic quantum number, is going to be a +1. And the spin in chlorine, sorry, not +1, it's going to be 0. And the spin of the chlorine, which is in this subshell right here, houses both a positive and a negative 1/2 electrons. So there are your quantum numbers for chlorine. All right. I'm going to zoom out a little bit. All right. Now, how do these 2 ions come together? So they've already made themselves a little happier, right, by getting rid of that extra electron or gaining the extra electron that they need, right, to form an ion. Sorry. Okay. So how do these 2 guys come together? When an ionic compound forms, we already see that they're going to bond based on opposite charges attracting. Okay. Sodium is a plus ion, right? Chlorine is a minus ion, and those 2 charges are opposite one another. What they're going to do now is they're going to come together to try and cancel these charges out. All right. The easiest way to understand this is here. I'm going to show you a little trick. Okay. When you form a compound, specifically an ionic compound, you want to try and get these charges to add up to 0. Now, lucky for us, 1 minus 1 already equals 0. Right? So what this is telling me is that I just need 1 sodium and 1 chlorine. The trick is that if you know the charges of the ions, the charges become the subscripts of the compound. And we're going to go over that in just a second. When these 2 guys come together to form a neutral compound, you're going to need 1 sodium and 1 chlorine. Now, because 1, like in algebra, is understood, you don't need to write the 1s. So this compound becomes sodium chloride. Okay, sodium chloride. Now, in a compound, the positive ion always goes first. Always, 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 always. Okay. The negative ion, which is in this case the chlorine, always goes last. Okay, or second. All right. So when you have a positive ion and a negative ion, the positive ion always, always gets listed first. Okay. To name it. All right. To name it. When we're taking a look at an ionic compound, okay, we understand that an ionic compound exists between a metal and a non-metal. Okay, so we're going to name these guys. We know that the metal always keeps its name. Always keeps its name. Okay, always keeps its name. Whatever the name is on the periodic table for the metallic element, it's the same name. Okay, the non-metal, okay, the non-metal adds a prefix, a suffix, sorry. Okay, the suffix is the IDE. Scroll up a little bit. The IDE. So if I have a compound that looks like this, sodium chloride, right? The metal is the sodium, so it keeps its name, right? And the chlorine goes from chlorine to chloride, right? Here's that suffix, all right? So when you're naming an ionic compound, you're going to use these rules to name it. The last rule is when naming or when using transition metals, you have to use a Roman numeral. To denote the charge. Hang on, let me scroll up a little bit. Because transition metals have more than one oxidation state, you have to tell me which one it is. But you'll see that as we go through a little bit more practice. Okay, so those are the rules. So make sure that you guys write these down in your guided notes. All right, so here's what we got. We got sodium and chlorine coming together to form a compound called sodium chloride. All right, we figured out that sodium is going to oxidize. We figured out that chlorine is going to reduce. Okay, and they're going to form this compound that's gonna cancel out those charges and form a neutral compound. Okay, all right. So here's one more practice. All right. My goodness, with these bells. Okay. So example, magnesium, all right, and phosphorus come together to form a compound. All right. I'm not going to go through the whole thing again. Okay. Always remember that metals are going to oxidize and nonmetals are going to reduce. Okay. So that should tell you with their electron configuration, okay, and their ionization energy, why these oxidize and reduce. But here's what we know. Magnesium is going to go from magnesium neutral and it's going to oxidize to form the ion magnesium 2+. Oxidize to form the ion magnesium 2+. Okay. Phosphorus is going to reduce to form the ion phosphorus 3-. Okay, so here's your cation and here's your anion. Okay, all right. Now, these guys have to come together to form a neutral compound, right? So they're going to bond together because the opposite charges attract. Here's the problem that we have. Magnesium is a 2+ and phosphorus is a 3-. So if I take 2 minus 3, I end up with -1. -1 does not equal 0. So we have to change these two guys so they both add up to 0. How do you do that? Well, if we multiply them by each other, let's say I multiply this guy by 3 and I multiply this guy by 2. 3 times 2 gives me, let's see, magnesium, that gives me a 6 plus phosphorus, 3 times -2, that gives me a -6. 6 minus 6 equals 0. Excellent. That's what we want. We want to make sure that these guys become neutral. So in order to do that, that means I need 3 magnesiums, right, and 2 phosphorus, right? This subscript tells you how many. This subscript gives you the number of moles, and we'll get to that later, of atoms. Okay, we'll get to the moles a little bit later, but just understand what they mean. They basically mean a quantity, all right? So my final compound then would be Mg3P2. The trick I showed you earlier works the same. If you take this number and you bring it down here, and you take this number and you bring it over here, you form exactly the same compound. Okay? Now, what is this guy called? Remember, the metal keeps its name, so that's magnesium. And the anion, or the non-metallic element, gets the IDE suffix. So this would be magnesium phosphide. Okay? All right, guys, I don't want to make the video too long. This is basically a gist of ionic bonding. We're going to continue this with another series of videos over covalent compounds and others. But for right now, please make sure you have your guided notes complete and then start working on your practice problems, okay? If you guys have any questions, just let me know.